Hey everyone, and welcome! Today, we're going to pull back the curtain on something we all use every single day, but maybe don't totally understand: the computer. We're going to break it down from its most basic ideas all the way up to the cloud. Okay, let's just dive right in.
Now, I know this sounds like the beginning of a really weird joke, but stick with me here, because it's actually the key to understanding, well, everything that follows. They both have to start with a plan, a blueprint, long before anyone lays a single brick, or in our case, solders a single circuit.
And this is where that skyscraper analogy really clicks. It perfectly illustrates the first huge concept we need to grasp: the difference between computer architecture and computer organization. So think of the architecture as the blueprint. It's what a programmer actually sees and interacts with. The instruction set, what kind of data it understands, it's all about the what the computer does. Organization, though, that's the actual building. It's all the nitty-gritty hardware details that make it work. Stuff that's totally invisible to the programmer, like control signals or what kind of memory chips are being used. It's the how the blueprint gets brought to life.
And hey, this isn't just theory. A classic real-world example of this was the legendary IBM System/360 family of computers. All of them shared the exact same architecture, the same blueprint. That meant a program you wrote for one machine would run on any of the others, no problem. But they had totally different organizations, different buildings, let's say. So a customer could buy a slower, cheaper model and then, later on, upgrade to a much faster, more expensive one without having to throw out all their software. It's the same blueprint, just a better, faster building. Pretty brilliant, right?
So no matter what the blueprint looks like, or how fancy the building is, what are the fundamental jobs that every single computer has to do? Well, it turns out it all boils down to just 4 things.
First up, data processing. This is the one we all think of, crunching numbers, manipulating data, doing the actual thinking. Then there's data storage. A computer has to be able to remember stuff, both for the short term, like what it's working on right now, and for the long term, like saving your files. Next, you have data movement. It has to get information from the outside world and send it back out. We call this input-output, or I/O. And finally, the 4th job, control. Something has to be in charge, managing all these other functions and making sure everything happens in the right order. It's the conductor of the orchestra.
Okay, so we know what it does. Now let's crack open that black box and take a look at how a computer is actually structured. We're going to start peeling back the layers from the top down.
When you look at it from a super high level, any computer, from your phone to a supercomputer, is really just a collection of a few main parts all working together.
So you've got the central processing unit, the CPU, that's the brain. It runs the show and does all the processing. Then you have the main memory, which you can think of as the computer's short-term workspace. After that comes input/output, or I/O. These are the computer's senses and its voice, the way it communicates with us and other devices. And finally, tying it all together is the system interconnection, which is kind of like the nervous system, a bunch of wires that let all the other parts talk to each other.
Now, of all those pieces, the CPU is hands down the most interesting and the most complex part. So, you know what we're going to do. Let's zoom in even further and see what's going on inside.
So if we look inside the brain itself, we find its own little specialized components. There's a control unit, which, like we said before, acts as the orchestra conductor, telling everyone what to do and when. Then there's the arithmetic and logic unit, or ALU. That's the powerful calculator that does all the actual math and makes logical decisions. And finally, we have registers. Think of these as a tiny, super fast little scratch pad that the CPU uses to hold the data it's working with at that very moment.
So we've got the logical structure down, but the physical story of the computer, wow. It is one of the most incredible journeys in the history of technology. It's a story all about unbelievable miniaturization.
The very first generation of computers used these things called vacuum tubes. And they were massive. I mean, they filled entire rooms and were incredibly slow. Then, the second generation came along and replaced those clunky tubes with transistors. These were a game changer, way smaller, cheaper, and so much more reliable. But the real revolution, the one that changed everything, was the third generation, the integrated circuit. This is where engineers figured out how to cram an entire circuit's worth of components onto one tiny little chip of silicon.
And this insane pace of progress wasn't just random. It was actually predicted way back in 1965 by Gordon Moore, one of the co-founders of Intel. His observation, which we now call Moore's Law, basically said that the number of transistors you could squeeze onto a chip would double roughly every 2 years. And you know what? He was right. And it completely changed the world.
Just to put this into perspective, let's look at the actual numbers.
Let's start at the beginning. In 1971, the world's very first microprocessor, the Intel 4004, had just 2,300 transistors. And at the time, that was a mind-blowing achievement.
Okay, now brace yourself. Fast forward to 2013. An Intel Core i7 processor had 1.86 billion transistors. No, that is not a typo. From a little over 2,000 to nearly 2 billion in about 40 years. That right there is the absolutely staggering power of Moore's Law in action.
So what's the consequence of this incredible shrinking act? Well, it means that powerful computers are now literally everywhere, often hiding in plain sight. This brings us to the age of the embedded system.
So where did all of these billions and billions of cheap, tiny, powerful computer brains actually go? They didn't just stay in our laptops and on our desks.
They went into what we call embedded systems. An embedded system is just a computer that has a very specific, dedicated job, and it's placed inside a larger product. It's not a general-purpose machine like your PC, it's a specialist, built to do one thing really, really well.
And you use dozens of them every single day, probably without even realizing it. Your car is packed with them, controlling everything from the anti-lock brakes to the cruise control. Your microwave, your washing machine, your digital camera, your home security system. Yep, they all have a little computer brain inside, doing its one specific job.
Okay, so we've gone from room-sized machines to computers hidden in our coffee makers, but the evolution doesn't stop there. The next major step was to make the computer's physical location almost completely irrelevant. So welcome to the cloud!
So what is the cloud, anyway? It sounds so mysterious, doesn't it? But really, at the end of the day, it's just a model where you get on-demand access to a massive, shared pool of computing resources over the internet. So instead of owning the hardware and software yourself, you're essentially just renting it from someone else whenever you need it.
This rental service kind of comes in three main flavors. At the very bottom, you have infrastructure as a service, or IaaS. That's where you're just renting the raw building blocks, the servers, the storage. A step up from that is platform as a service, or PaaS. Here, you rent the hardware plus the operating systems and tools you need to build your own stuff. And at the very top, you have software as a service, or SaaS. This is when you're just using a finished application that lives on the cloud, like Gmail or Netflix. So the key here is that it's all about how much of the computer's organization you want to manage yourself versus how much you want to just rent.
And that pretty much brings us to today. Think about that journey for a second. We've traced the computer from a blueprint to a physical building, to a microchip, and now to an invisible service in the cloud. We've gone from physical architecture to something that feels almost like magic. So the question I want to leave you with is this: what's the next layer? What comes after the cloud?